Okay, so this is basically the lab setup we had from the other day. We have a cart being pulled in sort of a modified Atwood machine, and the mass is kind of hanging from the side here, but this is really more about the analysis than anything else. The accelerations on here are already meters per second squared, which is a little bit different than how we did it in class. We do have to actually alter our grams on here to make sure that we can have this in kilograms. So for those of you that weren't here, essentially we have a cart, which I need to know its mass of, a hanging mass, which I have listed as its mass, and then any mass we add to the cart. And ideally, what we're trying to figure out is what is the relationship between mass and acceleration if we keep the force, due to the force of gravity, the exact same. All right, so first and foremost, we need to figure out the graph with the relationship between what I am changing, the independent variable, our mass, and then what's happening to the acceleration as that happens. Slight problem here. We need the total mass, not just the mass we add onto the cart, because the entire system is accelerating in what we call the positive direction. So I'm going to go ahead and click on this column B and insert just a column to the left. It's not really important which way that goes, but I'm going to call this one total mass. And I'm going to kind of jump start and go into kilograms because I know that by the end of this, I want to be thinking in force, and force is going to be in newtons, which is kilogram meter per second squared. I have my meter per second squared. I should need to make sure I'm actually in kilograms. For the total mass of the system, I would be including whatever's on top of the cart itself, and then of course the hanging mass. None of these are actually in kilograms, so I'm going to sort of add them up together, and then we'll divide by 1,000 to take it from grams into kilograms. What's nice about sheets is you can get sheets to do it for you. So we'll hit an equal sign. I want to add up A2, which in this case is 0, plus the 225 mass of my cart, plus the 250 mass of my hanging mass, and then that's going to end up giving me an answer in grams, which is not what I want. So if I take this 475, what I originally had here, I'm going to put this in parentheses, and then at the end here, before I hit enter, I'm going to hit divide by 1,000, so I can have this all in kilograms. Sometimes sheets will ask you if you'd like to do it for the whole thing. Sometimes it doesn't. So in this case, it didn't. I'm going to copy, I'm going to drag down, and I'm going to paste them all in. So now I've got my total mass and I've got my acceleration. If we want to just try and figure out our graph here, all we're going to essentially try to do is take this accelerated value, and we're going to use that as our y-axis because I changed the mass. If I insert a chart by using this as my actual series here, you hope to decide that it's going to pick some kind of chart. Sometimes it'll give you something random here. I need to actually have a scatter, which is a little bit of the way down there. And then it's got my range of C1 to C10. So that's the column I do want. What we want to change here is we need an x-axis. If we click here, there's a little box to the side. That little box will allow us to select what we want our x-axis to be. In this case, that's going to be the total mass. I'll hit OK. So now we have our first graph. And looking at this first graph, we can see from this data set, all right, this is decreasing. It is not a linear relationship. So there's a little bit of work to be had here. For the purposes of this lab, we were just trying to actually get the graph, and so we have this in place. Now we can mess with some of the customization features on here to get an axis actually labeled on there, so it does actually read as total mass in kilograms. I want to kind of bypass that. We know from what we've learned so far in class that this type of relationship is an example of an inverse. And we already know that because if we add more mass to the system, it should be accelerating slower. So as this goes up in terms of mass, the acceleration of the system is going down. So I'm going to manipulate that system and say, well, you know what? Instead of acceleration or mass versus acceleration, what if we worried about 1 over the total mass? Now that unit would be 1 over a kilogram, which is fine. We can get sheets to do this for us. So if I go ahead and hit the equal sign, I want 1 over whatever the value was of B2. And I can hit enter, and it's going to say, hey, do you want to do that for everything? Yeah, go for it. So now this entire column, column D, represents all of my inverses of my masses. And you'd think, okay, let's go ahead and set up an entirely new graph, which you can, and you can go through acceleration the same way we did. But we also can click on our existing graph and just change our x-axis. So when we click on our existing graph right here, I accidentally clicked in a spot that got us into customizing some chart labels. Setup is where we want to be. And in that x-axis, I need to get rid of this. Well, the 3 dots to the side allow you to remove the x-axis. Now I'm going to go ahead and pick a different x-axis. So I have my little box to the side here. Select all of this. And I've got now the 1 over x-axis. So this would be an example of linearizing my data, because now I've taken my data by looking at the 1 over aspect of it, and I have a straight line. Well, at least what appears to be a straight line. To actually check, we want to click on one of these dots, which will open up a customization feature in series. And if we scroll down, we'll see that trendline is an option. And inside of trendline, I want to go ahead and add a label to this. So we're going to use the equation, and I'm going to show the R squared value, because an R squared value is going to tell me how well that's meeting the trend line. Now, my data is fake, so my R squared value is awesome. It's exactly 1. Anything near 1 is going to be great data. When we look more specifically at this, we can see that our particular data, we essentially have the equation of y is equal to 2.21x plus, well, I guess that's minus a ridiculously small number. So it's 1.58 times 10 to the minus 15th. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 158. Or if we just think about it like a normal human being, that essentially is a y-intercept of 0. So we would just say, hey, there's our graphical equation. Now what's important to realize is it's not just y and x. Our y value was acceleration. So we really have acceleration is equal to 2.21 times 1 over our total mass. This is helpful because this looks an awful lot like acceleration of the system would be the net force of that system, all divided by the mass of the system. And if that's true, then this slope should be representative of our net force. Now, if you look back, our net force is all about the force of gravity relative to the hanging mass. My slope's 2.21, which says my system was going to have a net force of 2.21 consistently. Let's check what it should be. If the force of gravity is what we're really looking at, our force of gravity would be, our acceleration due to gravity times mass. And if that's the case, our force of gravity would just be 9.8 meters per second squared times, in this case, 0.25 to make sure that we're all good to go. Now I want Sheets to do it for me, so I'm going to cheat a little bit here. And I'll say, okay, 9.8, let's go ahead and multiply that by 0.25, and I get an answer of 2.45, which means according to my mass on here, 2.45 newtons worth of force should be pulling the system down. According to my graph, 2.21 newtons is accelerating my system into that direction as well. That's really, really close to what we're expecting it to be. And we could do a percent error on there, and we'd find like we're within 90% error, or 90% yield, or looking at almost less than a 10% error. But in looking so, this slope allows us to realize that we have figured out a new equation, and that's the acceleration of any system would be the net force of that system divided by the mass of that system.